Okay. Oh, well, yeah. Thank you for coming, and I guess I am getting a little predictable, and as usually, I will be talking about monads. Everybody knows that Bartosz talks about monads, but I will not be showing any Haskell code today. If you want to see some Haskell code, you can go to my website, and there is the same thing implemented in Haskell. So the origin of this is actually, I wrote a blog about this problem when I was preparing for this talk a few months ago. It just came to me. I read a blog by Justin Lee, which was in Haskell. He showed a very clever solution to this problem of constraint satisfaction, and I immediately thought, I can do this in C++. I can translate it in C++ and see how it works, right? So that's where the idea came from. So of course, the main question is, why monads? Why do we even bother doing this with monads? Because this is a problem that can be solved in many different ways, and using monads is just one way of approaching this problem. So monads, well, of course the question is, what are these monads, right? And it's really hard to explain. It's like everybody who talks about monads or first encounters monads has this moment of, I have no idea what these are. What's common among all these examples of monads, right? And then at some point there is this moment of to actually get the monad and write a blog about it. Try to explain it to others, and then everybody else reads this and they say, I don't understand. This is a very sort of spiritual experience, getting the monad. Okay, but I will try to explain it anyway. Okay, so monads are sort of a higher order control structures, right? I mean, we are used to different control structures, but they are usually built into the language, right? We have for loops, we have if statements, we have break, we have return, we have function call. You know, these are all control structures. They tell the program how to proceed, right? But there is a finite number of these, and they are built into the language. And monad generalizes this into all kinds of control structures that, you know, the designers of the language had no idea were possible, right? And it's an open set that can be created by users. Users can add their own monads to this and create new control structures. And the high level at which monads are working corresponds to this, monads are to loops, as loops are to gotos. Okay, what do I mean by that? Can you program without loops? Sure, right? I mean, you can use gotos. I mean, gotos are built into C++, right? So why do we need loops? In the same way, you can say, I don't need monads because I have for loops, or I have if statements, or I have exceptions, or I have other fancy stuff in my language that I can use instead of monads, right? And the thing is that it's the same you raise your level of abstraction by using monads to a certain level that's not available to you if you use the built-in control structures. And what are the advantages? One advantage is that when you use monads, your code becomes more declarative rather than imperative. Okay? And declarative programming is easier to do and easier to understand and easier to maintain, because it reflects what you are thinking about your problem. Okay? It describes the problem rather than, as it is in imperative style, telling the computer what steps to take. Okay? There's this big gap between what I think about the problem and what I tell the computer to do. And that's exactly the difference between, having a loop and having a go-to. A go-to is much lower level than the for loop. But for loop is still not declarative, it's imperative. And this code that is written in functional style using monads is much more reusable, and I will show you examples. Well, this is you will see in the process of development how reusable this code is, and is more composable. It's easier to compose pieces together when you use monads, and it's much easier to factor. In fact, factorizing is a huge problem in C++. C++ probably the hardest language to do factoring out of things. This is why, in Java you have all these tools that let you factor things out. In C++, there are very few, and they are very simple and primitive. And finally, maybe the most important thing is code that's written in functional style, in particular using monads, is much easier to parallelize. So this is all theory. Now I want to show a practical example. This is a simple example, so it can be solved in many different ways and not necessarily using monads, but on a simple example you will see how things actually work. So that's why I picked this simple example. So this example is a puzzle. Okay, you have a puzzle which each letter in this puzzle corresponds to a different digit from 0 to 9. Well, actually there are fewer numbers here than 0 to 9. They have to add up correctly. So if you form a decimal number out of these digits, they add up. Cent plus more equals money. And there's an additional condition that no number should start with a 0 digit. Okay? Sort of obvious. So how would you approach this problem? This is the brute force solution, right? And it actually, it would work in this example because the space of possible substitutions is not that huge. So you can actually go through all possible substitutions. So you would do this with these nested for loops, right? So the substitution for letter S could be 0, 1, 2, up to n. For each of these, you want to take a substitution for the second letter, E, and so on. So there are 8 different characters in this puzzle, so you will have 8 nested loops. Okay? Well, so that's fine. And at the end, you would check, okay, let me create these decimal numbers out of these substitutions, add them up, and see if they add up, right? And then spit out the solution, right? Now there was one condition was there that each character should correspond to a different digit, right? So you would probably have to add a little bit more checking here. So like S can be from anything from between 0 and 9, but E cannot be the same as S. So you would add this, right? N cannot be the same as S, and cannot be the same as E, and so on. So you'd have, I think, 7 of these more and more involved conditions, right? So this is already not very nice, right? I mean, we are adding additional conditions and the code is getting complicated, and it's easy to make mistakes, right? So a slightly better solution and more general is and faster is since we want to pick different numbers, then why don't we start with a list of possible digits, right? From 0 to 9, we have this list of digits, and when we pick a digit, we remove it from the list, right? So the next picker inside the loop will not be able to pick it anymore, right? So we go, we pick first digit, and then we remove it from the list, and we pick second digit, remove it from the list, and so on. So this is better because we don't have to check these conditions for, digits being different, and also we do fewer substitutions. The deeper we go, the fewer options we have. Okay, so we are already pruning some of the substitutions, which is a good thing. What is the problem with this solution? The problem is when we get to the bottom of this tree, right, and we find out, well, this is not actually a good solution. Or even if it's a good solution, right, maybe we want to find more if there are more solutions. This particular puzzle has only one solution. But in general, it's not true, right? So what do? Well, we have to backtrack, right? We have to put this digit back into the list and pick the next digit, right? So immediately we get, and this is how these things are usually done in an imperative style. You do backtracking, right? And that involves two things that we don't like. One is mutation, right? Removing stuff from the list, putting it back into the list. We are mutating the list. In functional programming, this is a big no-no, right? And if you want to parallelize this algorithm, mutation also is not your friend, right? It leads to data races. Okay, and the second thing is state. You have to keep track of state, right? Like, where am I? Which things in the list have I already tested so that I can move to the next one, right? So this list and the position in the list are the state. So we have like the worst things, and we were just trying to improve on our algorithm, and we have introduced like the worst things that possible. We introduced state, and we introduced mutation. Not a very good thing. So let's look for solutions outside of the realm of programming, right? And since I'm a physicist, I like quantum mechanics. And so what does quantum mechanics have to do with this? In quantum mechanics, you have this so-called non-determinism. Like, you perform the same experiment multiple times, you may get different results. That's non-deterministic experiment, right? And it's you can start with the same setup, the same experimental setup, and you get different results. Like when you measure the spin of an electron, right? The spin can be either up or down. You never know. You measure it once, it's up. You measure the second time, it's down. The only thing that we can predict is the probability that in 50% of the cases it will be up, and 50% of the cases it will be down, right? Everything else being equal. So quantum mechanics is non-deterministic, and there are people trying to deal with this in the beginning of the 20th century. They came up with these interpretations. One is called the Copenhagen interpretation, which says that when you actually do the measurement, the wave function collapses. Okay. But there is another very interesting interpretation that says when you are making an experiment, our universe actually splits. So it gives rise to two universes. In one universe, the spin is up. In the other universe, the spin is down. That's called a many-world interpretation of quantum mechanics. It's a serious interpretation. I mean, you cannot really experimentally tell one from another, because you always end up with one of these universes. Mm-hmm. Well, a copy of you ends up in the other universe, right? So this is we can try to apply this to our problem, right? And say, well, each of these substitutions creates its own universe, right? So like there is a universe in which S is 0, and there is another universe in which S is 1. And then, so once you are in a particular universe, then you have your whole future of solving this puzzle, but already S is fixed, right? And then the choice of the next letter, E, right, is creates still more universes, right? So you just go multiplying these universes, right? But of course, creating a universe might seem like, okay, maybe that's an overkill for solving such a simple problem, right? But the thing is that in functional programming, creating a universe is really cheap. Because, I mean, if you think about it, these two universes in which S is 0 and S is 1 are identical except for this one digit. So they share everything else, and you can just pass this digit, this single digit, as something that describes your universe, right? So you are just sharing everything with the previous universe except for this one digit. So it's really cheap. So now, the thing is that if you want to be able to create these universes, right? There is this one step when you are doing your experiment, right? You are saying, okay, now I'm in this universe, and given that I'm in this particular universe, this is my whole future, okay? This is the rest of my computation. The rest of my computation, provided that I have already picked an S, right? And then if I pick an E, well, then there is the rest of computation that already has S and E set, but there is this rest of computation that will give me the answer, okay? So that's the rest of the computation is called a continuation, right? So we have a choice, or actually a set of all possible choices as our input, and we have a continuation that depends on which input is current, that provides the result. Okay? So the only thing is we have to be able to glue these two things together. So given a set of all universes and a function that picks one universe and gives me the result, or not, because maybe in this universe there is no answer, or maybe there are multiple answers, right? I have to be able to glue these two things together. So this is my input, and this is a function that, given a particular input, produces a set of universes. So now we can write some code, right? This is very easily translated into code. I call this function for each for a sort of obvious reason, because it works just like a loop, but it's not, right? And it's a function that takes a list. So in our cases, the list of universes is the universes of type A, right? In our cases, this will be just integers, a list of integers. whether it's 0, 1, 2, 3, and so on until n, and takes a function that is the continuation. And this function takes an argument of type A, so one of the digits. So suppose that you have chosen a digit for s, right? This tells you how to, given s, given the value of s, how to get the result. So this is sort of like, recursive thinking, Now I have a simpler problem to solve. This continuation solves this simpler problem and produces all the results. Possibly multiple, maybe 0 results, right? And the implementation is really easy, okay? So you just have to call this continuation for every element in the list, right? For every possible universe, the input universe, you just call this continuation, and this continuation produces a bunch of outputs, right? Which is also a list of some b's, right? In this case, a list of solutions, right? And if you apply this continuation to an element, you get a list. If you apply it to the whole list, you get a list of lists, right? So now you want all these lists, you want to concatenate them to get just one big set of universes, your output universes, right? So that's the function concat all. It concatenates a list of lists. Fmap here is sort of like standard transform, right? Except that it does not modify its input. It just creates a new output. Just applies a function to each element of the list, creates a new list with the results. In this case, the results are also lists. Okay? And the final thing is that this list here, that's actually a data structure. It's a singly linked list, but it's a persistent data structure. A persistent data structure is non-mutable, immutable. Okay, so it never changes. The only operations you can do on this list is add something in front of it, or you always, whatever operation you apply to it, you get a new copy of the list with this change applied. Okay. Now, normally you would say, okay, this is really, really wasteful. So if I want to add something in front of the list, I will have to copy the whole list and then add it. No, actually, because your original list is immutable, you don't have to copy it. You just have a pointer to it. Okay? So persistent data structures are such that they are immutable. They are persistent because they always have a previous copy. The previous version of the list persists. It stays there, doesn't disappear. So when you do a mutation, your previous version of a variable disappears. It's replaced by the new version, right? Here you keep all the versions. Why do we want to use a persistent list here? Because we don't want to do backtracking. Okay? If we have a list that never changes, then backtracking is not necessary. Because the previous version of the list remains. Okay? So I don't have to put stuff back into it. I just go back and the list is there. Okay?
So does it mean that the space complexity of the algorithm is increased?
No, actually adding something to the front of the list is O1. Because all you are doing is creating a new node and a pointer to the previous list. Right? Now, what is complex in this thing is garbage collection, right? Because now you have multiple pointers pointing to the same tail, and this is when you start using shared pointers. Okay, I have a set of blogs about persistent data structures, and they are very popular in functional programming. All functional languages use persistent data structures. And I have a library of these things. So I was just reusing what I already have. So if you look at this function, okay, this is easy to understand, right? It's parameterized on two types, A and B, right? You get a list of A's and you produce a list of B's, right? Unfortunately, if you try to use this in your code to do this for each, you will have to, when you call it, you will have to specify these types, or at least the type B, right? Because C++ compiler is not smart enough to figure out the types by itself. Type inference in C++, even with auto and so on, is really, really primitive compared to functional languages. So if you want to avoid this, this is what you really have to do. Okay, so you instead of parameterizing it by A and B, you parameterize it by type A and F, which is the type of the function that you are passing. And also, this is more efficient because you're not converting everything into standard function, which is an expensive process. Here, it just you get an inline expansion of this. Right? Well, it produces more code, but it's more, but it's faster, right? But because the compiler cannot figure out the types, you have to provide them. So you do this trick with decal type. You get the auto return type and decal type, and then you tell it what type will be returned by this function. Okay, so that's a standard C++ trick. And here I added some static assert also, which really in C++ 17 will be replaced by concepts. But it's possible right now, so this thing works. Okay, there's another thing that so we have this for each actually will bind the previous selection of multiple universes to the continuation. And if you think about it as these nested loops, I call it for each because it really corresponds to a nested loop, a series of nested loops. The continuation is like all these internal loops, okay? But at some point, you have to end this recursion, right? At some point, you have the result at hand. You checked, okay, these digits are actually working. You want to stop the recursion and send it back. And in order to send it back, you have to have this sort of trivial function that produces a singleton result. This is my result. I already have it, and it's only single, and it's called yield. I will rename these functions later because every monad actually has these two functions, and so there is a common name for that. But this is like your first approach to monads, so it makes sense to look at it as this is a loop. Okay, this is sort of like a loop, except that instead of iterating, it takes a whole list of inputs, right? Instead of iterating I equals 0, I equal 1, I equal 2, and so on, it just takes a whole list of all possible things, right? And for each of them, calls the continuation, which is like the body of the loop, okay? And at the end, it returns the result. So this returns a singleton list. Now, with these two functions, okay, we define these two functions define what is called a monad. Okay? One is a way of composing the result of previous computation with the rest of the computation. And usually in functional programming, this is called bind. Okay? And the other function is just to, when you already have the result, you encapsulate it into the list, or in this case, into a singleton list, right? So this is a way of trivially returning something in the same way as every other function. Okay? So since this is based on a list, it's called a list monad. And as you can see, a list monad corresponds to this idea of a function returning multiple results instead of one, or creating multiple universes. The idea of non-determinism. It's a function that might return this or that or that or that, right? And it's encapsulated in a function that returns a whole list of possible results. So list of all possibilities. And this is, you're not supposed to understand this yet, right? But this is how this whole program would look like. And it's kind of very similar to the set of nested loops. Maybe I used a little weird indentation for this. But the idea is this, that you use this for each to bind. Think of cell as being a list of possible substitutions for the first character, right? So there are it's a list of 10 different substitutions. For each of them, bind it to a continuation. So this continuation is a lambda, right? So this is a lambda that captures the environment by value, the equal sign, right? So it takes one argument, and it takes the value for the first character s, okay? And the body of this lambda goes to the very bottom of this function. So this whole for each, or this list monad for the branch, right? But there's the second part. The second part is related to the fact that we have this list of possible digits, and we have to be passing it, shrinking it, and passing it lower and lower and lower, right? So this is the second dimension. This is the depth dimension of our search. So here's this process again, right? We start with a list, and we are passing the shrinking list from one stage to the next. And you can think of this, so normally, so this list could be thought of as some kind of state of computation, right? From stage to stage of the computation, this list is shrinking, and we are progressing through this list. Now we don't have to progress through this list anymore, because we have our list monad. The list monad deals with the fact that we don't have to iterate through this list. We're just applying our continuation to the whole list, okay? So we don't have to iterate anymore. I mean, there is iteration somewhere down there in the implementation of fmap, right? But we don't care about this. For us, it looks like you get the whole list, apply the continuation to the whole list. So we don't have to remember where we were anymore. This is something that's done inside the fmap. It doesn't percolate to this level. So that's a great simplification. But now we have to deal with this fact that we are passing this list along. And we could, so changing the state, normally, I mean, how would you do this? You would pass an object with the state, or maybe have a global variable with some state, and your functions would be changing it, or so on, right? These are not very good solutions. This can be done with pure functions without any mutation if you consider dealing with functions that take the state, which in this case is the list, as an input together with whatever other input they need, and return this list together with the output. So you can have, instead of dealing with functions that go from A to B, you are dealing with functions that take a pair, A and list, and return B and list, right? And this list may be different from this list, right? I mean, it's a list of integers, but it could be shorter, or maybe the same, right? Or maybe longer, right? So this imitates the way we are thinking of changing state, right? We are saying, pass me the state, I will give you a new state. Doesn't mean we are actually modifying the state, because again, this list is a persistent list. We never modify it. So whatever list you pass to me is still available for you, right? But you have a new copy of this list with a change that's being returned. Okay? So this is very important. The combination of persistent data structures with this is very important, because you never have to do any backtracking. And here's a trick that is very, very well known to all functional programmers, and it was already mentioned here. It's called currying. Okay? So, first of all, think of this function. Okay, so this is a function that takes a pair and returns a pair. Think of this as a function that takes two arguments rather than a pair, right? Whether it takes a pair or two arguments, it's the same thing, right? So it's a function that takes two arguments. And a function that takes two arguments can be always thought of as a function that takes just one argument and returns like a temporary function that still expects the second argument. Okay? And that's called currying. So instead of dealing with these functions that take pair and return pair, we can deal with functions that take just the first argument, the A, right? And return a function that expects a list and produces a pair of B and list. See this flip? This is kind of weird thing of thinking, weird way of thinking about this problem. And it turns out that dealing with these kind of functions is possible because starting with C++11, C++ actually can deal with functions as first-class citizens. So we can have functions that return functions. We can combine these functions. We can modify these functions. We can return functions. We can take functions as arguments, right? So let's try doing this thing with these curried functions. So the problem now is like this. Instead of doing our calculations in these loops, right? Why don't we just create functions and pass them on? Create functions that expect a list and produce a list together with some answer. Okay? And let's try to glue these functions together to produce like the final function, okay? Which will be our solution. But it will not be a solution because it's just a function. And at the end of this, we will say, okay, this computation produced a function. Let's call this function, let's give it a list of digits from 0 to 9 and see what it produces. Okay? And it will produce the answer plus the leftover list. Right? If there is any. Well, there will be 3 more elements in this list. So this kind of thinking is very similar to planning the future. Okay? because you're not saying I'm doing this and I'm doing this and then I'm doing this. It says I have a plan to perform something if I have some input. Right? So, for instance, if I had lots of cash, I would buy a car. And then I would still have some leftover cash. So this cash now is my state. Like I had a list before, now I have cash, right? So a plan to buy a car is a function that takes cash and returns a pair, car and cash. Okay? So you see these functions that take some argument that take state and produce a result and a state. So I call them plans. Okay? So instead of dealing with some computation, why don't we just create a plan to deal with a computation? Right? And then there is a special case of a financial plan, which is I already have it. Right? I have a car, let's say. No, sorry, this is, I'm jumping ahead of myself, right? So this is a generalization of this stuff for any object, A, instead of car, right? So it's a template that's based on object A. I can have plans to produce different things. I can have a plan for a car. I can have a plan for a trip around the United States, and so on. So all these plans have the same form. These are functions that take cash and return a pair, A and cash. So that's my general financial plan data structure. Now let's, okay. So the most important thing is how do we combine these plans? Right? If we want to have a monad, and this is where I'm driving it, is how do we combine plans? Okay? So suppose that I have a plan for a trip around the United States. But this plan requires a car. And I don't have a car. So instead I have a function that, given a car, can produce a plan for the trip. And I can give it different cars, right? Depending on whether I buy a cheap car that has very good gas mileage, or I buy some car that has very bad gas mileage, and so on. The plan will be different because I will have to stop at more gas stations and pay more money for gas, right? So this plan will depend on what car I give it, right? And I don't have a car, but I have a plan to buy a car, right? So I can have, I have a function that, given some amount of cash, will give me a car and the leftover cash, right? So this is my car plan. It's a function that returns. It's a function that takes cash and returns car and cash, right? So how do I compose these two? Okay. Think of this car plan as the input, and this as a continuation. Okay? So how do I compose this? Well, as soon as I get some cash, I should execute the car plan. That will give me a car. Then I can call this function with this car, and this will give me a plan for a trip. And then I can execute this plan for a trip. But with what cash? The plan requires the cash, right? Mm-hmm. With the cash that was left over from the first plan, right? Yeah. After buying a car, I have less cash. So I pass this cash to my plan, and then I go on a trip.
But why the ampersand? I don't understand.
Oh, well, it doesn't have to be.
Oh, okay.
I just like putting ampersands when I take an address.
Okay.
Right? But you don't have to put an ampersand if you take an address of a function. That's true. So now the same thing, but not with cars and cash, but going back to our example, our state is a list of integers. That's the list of available integers from which we are picking, right? And the plan in this case takes a list of integers and returns some value, whatever was calculated, and the leftover list of integers. Maybe it's the same list, maybe it's not. So an example of such a plan is pick one integer, okay? That's a plan. Give me a list. I'll pick an integer from this list, and what do I return you? I return this integer, that's my A, and the list without this integer, the leftover list. Okay? So that's a perfect plan. Takes a list, returns a pair, value and list. Okay? So this is like one of these plans that I can use in solution of this puzzle, right? And finally, when I create a plan, a big plan to solve my puzzle, then I can call this plan with a list and get a result. So I need this function run plan. Takes a plan, takes some state, and just calls this plan with the state. And then returns a pair. That's your result, and that's the leftover state. And this binding that I talked about, combining two plans, combining a plan with a continuation that also produces a plan, can be expressed in code, right? So my input is a plan that produces some A, and I have a continuation that takes an A, okay, and creates a plan to produce B. Okay? So how do I do this? So think about, I have a plan to produce a car, to make a car, and I have a continuation that given a car produces a trip, right? And I said how to do this, right? So since this function is mbind, now I call it, okay, must produce a plan, and the plan is a function, so this function has to return a function, right? Okay, so how do you return a function? You return a lambda, right? So I'm creating a lambda, I'm capturing this plan and this function, and it will be I have to return a plan. So a plan is a function that takes state, okay? So it takes a state as an argument. Now inside this lambda, I have a state. So I can run my plan, the first plan, so that's the plan to buy a car, right? With this cash, and I get my car and the leftover cash, right? Then I run my continuation with PS first, that's my car, okay. And I get a plan for a trip, right? Now with this plan, I can run this plan, plan B, right, with the leftover cash, which is the second part of this pair. Okay? And it works. And what the important thing is that I can combine plans, right, without executing them. Because I'm not executing anything here in mbind. I'm just creating a function that will execute these things later. When the state is provided, when the list is provided or the cache is provided, right? So I have a way of gluing functions together that produces new functions. Okay? That's a weird thing. This is not a weird thing for functional programmers, but for imperative programmers that might be interesting. Finally, there is this trivial plan, the I got it plan. I already have a car, right? But I need, for my code, I need a plan to give me a car, right? So that you can create this plan very easily. Okay, it returns a function that takes state, right? Doesn't modify the state at all. It just returns it back because I don't need a cache. I don't need cache to get a car that I already have. And I just pair it with my car, this leftover cache, and I'm done. So that's my trivial plan. Now these two things, I don't know if you see this, but they have the same structure as our list monad. And this is called the state monad. There's a way of composing calculations, and there's a trivial computation that returns a trivial thing. Okay? So that's our second monad. Now all we need is to combine these two monads. And I will not go into the details of this, they are in my blog. But I'll just give you the general overview, right? So I have to combine these two things. So I have to combine the fact that I can have multiple choices and the fact that I will actually not produce these choices right now. I will just give you plans to produce these choices. Okay? So the state, again, is the list, as before, right? But I will produce lists of pairs with result and state. So each choice from the list, for instance, will return a new pair of this digit and the leftover list. Right? So I need a list of these guys. So my state list is a combination of these two things, the list monad and the state monad, in the sense that it produces a function, so it produces a plan, right? But it produces a plan that when given a state, it produces a whole list of pairs, not just one. Okay? I mean, this takes a little bit of getting used to, and you should probably go over it several times before it clicks. But that's a very simple combination of these two orthogonal things. You know, being able to have state and producing multiple results at the same time, right? So this is the implementation of this picture, except that the list will be provided at the end of the computation. Once I have combined all these computations into one big plan, then I will provide it a list, I will give it this list, and it will execute and go on like this. And in fact, there is a little bit more to it, because I also have these conditional stuff and so on. So really the state list is not just a simple monad, it's what's called a monad plus. Okay? Like every monad, it has this bind or mbind that is used for composing things, right? There is also, I mean, in other languages you don't need this, but in C++ you need this special case mthen, which is same as bind, but it's just calling a continuation that disregards its argument. So like you have a function of void, which is important here because even though it disregards the result, it does not disregard the state, right? So it passes a different state to the next computation. Then you have this mReturn, which is a trivial computation. And then because it's a monad plus, it has this guard implemented, which just calls the continuation only if the condition is true. So this is how you can check a condition and then call the continuation or not. So that's the decision point that you make. Okay? And now you can sort of understand a little bit better this code. This is the same code, but with mbind and mReturn and guard. Okay? And what you see here is this cell here. This is this selection. This selection is actually different every time you go inside, right? Because when mbind is being executed, what happens is it takes a list, removes something from this list, and passes it to the continuation. And this continuation calls cell again. But this cell will get a shorter list. So it will not select the one that you have already taken out. Okay? So even though it looks like it's the same selection, it's not. Okay? Because the state is changing as you go. Okay? So finally, at the end, you have this guard, right? That S is different from 0 and M is different from 0, which will call discontinuation or not. If this is false, it will not call discontinuation. If it's true, it will call this. It will convert these things into decimal numbers. Then we'll call another guard to check whether they add up, right? And call discontinuation or not. And if it calls discontinuation, then this one will just combine these three numbers into a tuple and return a trivial plan to produce this tuple. Okay? So that's how it's used. And here's the conclusion. Okay? So first of all, this is just a simple example, right? But the problem of solving constraints is much more general. Okay? So this technique can be used to solve much more complex things. And the fact that it was written using functional code and monads in particular makes this code, first of all, reusable. Okay? Because I can take these monads and I can put them in the library. And then they can be used to solve lots of different problems. Monads also are very good for creating libraries, because a monad, as I showed you, is about composition, right? I mean, like the main function there, the mbind, is for composing things. And a library, when you are writing a library, this should be your major concern. How this library composes. You are giving the user something that they will be using in different configurations, right? There's not only one way of using the library. They have to be able to compose elements of your library in different ways. You are giving them Lego blocks and they have to build buildings or cars or whatever, right? So they also have to combine their code with your library, right? They have to be able to plug in their code, the user code, with your library. They have to be able to plug library code into user code. So that's also composing code, right? And because monad is the essence of composition, the libraries that are monadic are very easy to compose. And this was the major mistake that was made in C++11. Because C++11 introduced futures, which are monads, without realizing that there are several parts missing. Okay? This is what C++17 is going to solve. The new futures will actually be monadic, and they will be composable. Right now, futures are very, very hard to compose. Okay? And another library that's built on these ideas is Eric Niebler's range library. Unfortunately, Eric Niebler is my friend, and I talk to him like every week, and we talk about Haskell and category theory and so on. So he's the right guy to write a range library, and it has a lot of these elements of monadic goodness. So what I would like to see in the future, I don't know if this will happen, to have a library of monads in C++, right? And also, it would be nice to have better syntax for them. I mean, if you look at this code, it's kind of ugly. I mean, all these continuations inside continuations inside the continuations, you know, like in functional languages, monads are used with special syntactic sugar so that they look very nice. C++ doesn't have this syntactic sugar. But there is a proposal called resumable functions to provide syntactic sugar, but only for one monad, for the future monad. Okay. Will there be another syntactic sugar for the range monad? Will there be yet another syntactic sugar for the optional monad? Optional is also a monad, and so on. And what about user-defined monads? Like this one, right? So this is my hope that, you know, I'm evangelizing monads to every C++ meeting in this hope that somebody will pick this up and introduce them into C++ in the right way, instead of repeatedly going with hacks to solve one particular problem and then another particular problem and so on. Okay? Thank you. So all this stuff is available in my blog and on GitHub. Please look at it in your free time. Okay? Domande?
Due domande. C'è la domanda.
I just want to make sure I understood the connection between the two parts you had. So if I'm correct, it was
the list monad, right?
Well, the cache car and the actual problem you talked about.
Oh, okay.
So let me say what I understood, and you say if it's correct.
Okay.
So the cache is essentially the list of remaining integers as the state, and the car is the correct integer you pick for one number in some sense or something.
Okay, so this is a template really. So it could be a car, right? Or it could be a trig.
Yeah, okay.
In this case, it could be in the next digit that was picked, or it could be the result of the whole computation, the 3 numbers.
Okay, I see.
Right?
Okay, close enough. I was close enough.
Okay. Yeah, no, that was good. Yeah. Any more questions?
So I just wanted to know if you have a suggestion for someone who had never approached functional programming, someone was always used imperative programming. Is there any recommendation about books or articles to get started properly with functional programming? And
You just got a book, right? You want a book.
So starting to learn Haskell is a good way to get started with
I think it is. I think it is the best way to start
for C++ programmers.
For C++. That's how I started. You know, I was doing C++ for so many years, and then I started doing template metaprogramming and trying to understand it. You know, and I realized that I just can't deal, first of all, with the error messages. Second of all, I can't deal with the complexity of the stuff, with the syntax of templates. And finally, it occurred to me, you know, compile time, C++, the templates, they are a functional language, right?
Yeah.
So why don't I learn a functional language, just elements of it, you know? And I started learning a little bit of Haskell here and there, and I started understanding this stuff.
Okay, thank you.
Grazie.
Grazie.